Good morning, everyone, and welcome to the first sunny day of this summer school. So we're starting a bit early today to celebrate that, of course. And without any delay, I'm going to invite Thomas to talk about how to evolve dynamical spacetimes now that we have learned how to create initial data for it. Thomas.
Thank you. Thank you. And welcome back, everybody, indeed, on this beautiful morning. So this brings us to Friday. This is the last day of the first week of the summer course and also the last day of my lecture series. So let's just retrace what we did. Essentially, we spent a long time talking about 3+1 decompositions of theories. We applied that to general relativity. And what we've seen is that in such a 3+1 decomposition, we split the field equations into a set of constraint equations and a set of evolution equations. Yesterday, we talked about how we can solve the constraint equations. By solving those, we basically get valid data on one slice of time, one time slice. We can use those as a set of initial data. Now the question is, how can we evolve those data into the future? And we do that by solving the evolution equations. That's exactly what we'll talk about today. All right, so this brings us to our last chapter here. This is chapter number 4, solving the evolution equations. So again, let's assume we have done what we discussed yesterday. We've constructed some set of initial data. Maybe it's 2 black holes in a binary orbit. It might be neutron stars. It might be something completely different. It doesn't matter. Basically, we're assuming we now have a set of initial data, by which we mean we have basically the spatial metric and the extrinsic curvature at some initial time t equals 0. Okay, so now we want to evolve those, okay, with the evolution equations. So basically, we could look at our notes from Wednesday when we wrote down the evolution equations. We saw that the time derivative of the spatial metric is -2 alpha kij plus the Lie derivative along the shift of gamma ij. And then we had the second equation for kij, which was alpha rij minus 2 kik kkj plus kkij, then a minus di dj alpha plus the Lie derivative along the shift of the extrinsic curvature plus what I'll just write down as matter terms. Okay, so we could look up what exactly those are if we have matter in our space-time. For vacuum space-times, like black hole space-times, those would be absent, of course. Okay. Remember, we relied a lot on analogies with scalar fields and ENM. And basically, we saw that the structure of these equations is very similar to that we found for the scalar fields, as well as for the electromagnetic waves. In each case, we had the time derivative of our fundamental variable is basically a second variable, and then the time derivative of that second variable, it involves second derivatives of our fundamental variable, our fundamental quantity. In this case, these second spatial derivatives are hidden in this Ricci tensor Rij, right? So basically, think of this Rij as being a shorthand notation for these various mixed second derivatives of the spatial metric, all right? Okay, so far so good. We could be thrilled. We said, okay, we know exactly what to do. We basically now put these equations on the computer. How exactly do we do that? You will discuss that next week. There are different techniques that we could use to do that. There would be finite difference techniques. There might be spectrum methods. You know, there are other methods. So basically, there are various different numerical techniques how we could do that. We'll set it as that aside for now. We just assume we could basically find some numerical code, or we could code up these equations essentially and have the computer solve them for us. Okay. Now you could say, or you could object, but wait, we haven't talked at all about what to do about the lapse function alpha and the shift vector beta. Okay. True. Let's postpone that for a few minutes. It is absolutely true. We would have to make choices for those gauge variables, which tell us how the coordinates evolve. Okay. And we will talk about that, but let's postpone that for a minute. Okay. So then we say, okay, great, now let's evolve these equations. And well, guess what? I have good news for you and I have bad news for you, okay? The bad news is that if you tried to solve these equations on the computer, at least generically, basically for, in the most general case, the code will crash and die a violent death, okay? It will not work. Okay, that is the bad news. The good news is we also know how to fix it. So we will talk today first about how we can manipulate these equations so that numerical implementations remain stable, okay? And so basically, let me write this down, okay? So unfortunately, experience has shown that numerical implementations of this ADM system, okay, or the ADM equations are generally unstable. Okay? There are exceptions where it is stable, but generally these are unstable. Okay? But we have a way, or we found ways of reformulating these equations so that the reformulations are stable. Now you should ask, okay, what the heck do you mean by a reformulation? How can we reformulate these equations? And really, we have two tools at our disposal. One thing is we could introduce new variables. We could introduce new auxiliary variables, maybe derivatives of variables that we already have, and then maybe those derivatives we declare to be new independent variables, so we basically derive new evolution equations for them. Okay? So that is one tool that we could use. The other tool is, remember, we have equations that are redundant to these equations, the constraint equations. So I could also add multiples of the constraint equations to these equations, okay? And by doing that, I could develop all kinds of different reformulations, okay? What you should ask now is, how could that possibly help? Okay. But actually, you know what? Before we answer that question, maybe I should write down what I just said before we get too carried away here. Okay, so basically we have two tools. But we have found reformulations that work. Okay. And how can we, basically, what do I mean by reformulations? Okay, how can we derive a reformulation? Well, as I said, we can introduce new variables and we can add multiples of the constraints to the equations, to the evolution equations. Right? The constraints must be satisfied for any valid solutions. Okay, so basically that means I can add them as an equation to the evolution equations. You with me? Does that make sense? Okay. So again, now let's ask the question, how can that possibly make a difference? Because you could argue that, let's say we want to derive a solution to this system. Let's say we have an analytical solution to this system, or a valid solution, maybe I should say. Okay. Now we do all these reformulations, and guess what? That solution should still be a solution, right? Unless we made a mistake, which let's assume we didn't. Okay. So basically, an analytical solution to our original system must also be an analytical solution to our new system. So how can this make any difference? Okay. And the key in understanding that is that we should not think about the solutions. It is true that the solution to one system will also be a solution to the other system. What we should think about is the numerical error, any deviation from the solution. Okay, so basically, and it turns out that errors behave differently in different systems, and that helps us understand why one system might be stable, because maybe the error decays, whereas another system might be unstable because the error grows. Okay. All right? Yes? So why is that? Okay, wait. So why exactly does it blow up, the solution? Or hold your thought. Okay, so let me answer that question by by going through some arguments that show us why it is that basically one system may be unstable, another one is stable. Or strictly speaking, what I will show you is we can see basically why errors behave differently in different systems, and that will help understand that question. Okay. Now, one theme that you've probably picked up in this week is that I like using analogies with scalar fields and E&M. So we'll do that one more time, one glorious last time in this week. We'll actually invoke scalar fields and E&M to understand that issue, okay? And that, I believe, will address your question, okay? All right, so let's go back. Let's talk about the scalar field. So for the scalar field, we wrote down these equations like this. Okay. Minus kappa, and then we had a partial t kappa equals minus di psi plus 4 pi rho. Okay. And again, I want to impress on you the similarity with these sets of equations, right? We have the first time derivative of our fundamental variable is the negative of a second variable, which we just defined to be the time derivative of that. And then the other equation gives us the time derivative of this variable equal to second derivatives of our original variable. Okay, it's the same structure. Again, remember here, the second derivatives are hidden in the Ricci tensor. Okay. Now, what kind of an operator is this? It is the Laplace operator. Now let's think back. Let's think back to, I think it was on Tuesday when we wrote down these equations. Where did this operator come from? It came from the field equation for the scalar field, which says that basic psi satisfies a wave operator. Okay, so remember that? Okay, so basically by psi satisfying a wave operator, a wave equation, basically, then we brought the equation to this form by introducing kappa as a new variable. So basically, this being a Laplace operator is the consequence of psi solving a wave equation. Okay, so basically, let me write this as saying this is the Laplace operator. Okay, and this is inherited, if you want to, from the wave operator that psi satisfies, that is the field equation for psi, right? Okay, now wave equations, if we talk to our mathematician friends, that they would tell us that wave equations are hyperbolic equations. In fact, a special type of hyperbolic equations is symmetric hyperbolic. The beautiful thing about symmetric hyperbolic systems is that basically their existence laws, these systems are well defined, and we are guaranteed that they're solutions, okay? And basically that means we can also solve these equations numerically. I told you that already on Tuesday, okay, not with those words, but I told you basically if you have an equation of this form, we can solve this numerically. We should not encounter any problems, okay? So far, so good, all right? Now let's step up one rank. Let's go to E&M. And we'll just write down the equations in the simplest form for Minkowski space, where we found them to be partial AI equals minus EI minus partial I phi. And then we had a partial TEI equals minus DJ AI plus DI dj aj minus 4 pi ji. Okay. All right, we saw this equation before. We noticed before that in contrast to the scalar field, we now have a second term that contains second derivatives. This term is again the Laplace operator. What is this term? It's the gradient of the divergence, okay? So we have the mixed second derivatives switched, okay? If you think about the Ricci tensor, okay? Actually, there's different ways of writing down the Ricci tensor, right? Usually in the GR course, the form that you write it down is in terms of first derivatives of the Christoffel symbol. And actually, if you look at the sheet that I gave you with the results, I'm not sure whether you have that in front of you, basically, but the first, I give you 3 different forms for the Ricci tensor. The first form is exactly that one with partial derivatives of the Christoffel symbols. But then the second form is in terms of second derivatives of the metric. And if you look at that, you see there are 4 of those second derivatives, which I think we also wrote down already. And they are also all the kind of mixed, different ways of mixing those indices, kind of just an extension of this. Okay? But now notice something. If it were only this term, without this term, then we could make the same argument. We would say, oh, okay, the Laplace operator, really that is inherited from these variables satisfying the wave equation, and we would be all set. Okay, but that's not the case. We have this extra term, and this extra term spoils the mathematical properties of the system. Okay, that means that AI no longer satisfies a simple wave equation. That means the system no longer has these properties of symmetric hyperbolicity. We're no longer guaranteed that they're solutions. Okay? Now, does that answer or begin to answer your question? Okay, good. All right, so basically let me write this down. Basically, this term now spoils the characterization as a wave equation. Okay? And I'd like to refer to this term as the term of concern. Okay, that's the term that we should be worried about. Okay. Now let's check how constraint violations actually behave in the system. Okay, and in order to do that, I will want to make one more comment before we do that, because you could argue the following. You could say, but wait, there's no issue here. Because haven't we talked the whole week about gauge freedom? Right? There's a gauge freedom in ENM. In fact, what is a very common gauge choice that you make in ENM? And what does that? How do you impose that? What does that yield? It tells you that the divergence of A is 0. We can make a gauge choice to get rid of this term precisely. That seems like a very smart thing to do. Okay, but I don't want to do that here. Not just because I'm stubborn. Okay? No, I'm kidding. Because in ENM, that would be a perfectly fine thing to do. Why would we not want to do the same thing in GR? Because by doing that, we would throw out our gauge freedom. It means we would have used up our gauge freedom for bringing the equations into a form that we like. But now we don't have the gauge freedom anymore. And as we'll see in a little bit, is we want that gauge freedom so we can choose coordinates that are well behaved, for example, for the simulation of black holes. So I don't want to use up the gauge freedom. Okay, we recognize we could use it here, but we won't. Okay, we'll come up with a different trick. Okay, now let's check how do errors behave? And I'll measure those errors by looking at constraint violations. So let me start by defining a constraint. Yeah, question there? No, okay. A constraint violation. Okay, and maybe I'll call it C, and I'll define C as the difference between the left-hand side and the right-hand side of our constraint, Gauss's equation, all right? And we can now check, basically, what is the time derivative of the constraint? Okay, how does the constraint evolve if, let's say, we had a violation of the constraint in our system? So let's compute the time derivative of the constraint. Probably this is an exercise that you did in an ENM course at some point, or if not, you will do it, okay? This is how we could do it. I could take the time derivative of these two terms. Basically, in the first term, I can commute the partial derivatives with respect to time and the spatial derivatives. That gives me di partial t ei. And then I have a minus 4 pi times the partial derivative of rho. Okay. Now I can insert the evolution equation for E and replace the partial derivative of EI. That gives me 3 terms. Okay, let me work on the first two. The first two would be a minus dj. Then I have a dj upstairs, a di downstairs, and I've already commuted permuted the derivatives. And then I have an ai here. And then in the second term, I do something similar. I will get a plus di, dj, aj, okay? And then I have a minus 4 pi j, or the minus 4 pi, and actually the derivative of j, the di ji, and then I still have the partial derivative with respect to rho. Okay, so when you check my indices, I hope I got them right. But basically, I permuted the derivatives, okay, which I can do in flat space. We're doing this in Minkowski space. And then you see that this is now the Laplace operator acting on the divergence. And this is the same. Again, the Laplace operator acting on the divergence. So these two terms cancel. And how about these two terms? Have we seen this expression before? We did. What is it? It's the continuity equation. It expresses the conservation of charge. So as long as charge is conserved, this term is also zero, meaning this whole time derivative is zero. Okay? This was previously presented to you, if you've seen this before, as good news. Because what it means is that the constraints are consistent with the evolution equations, i.e., if you have initial data that satisfy the constraints, meaning that C is zero, if you now evolve them with these set of equations, then the constraints will remain zero analytically. Okay? That is true for an exact solution. Okay? So basically, usually this argument tells you that the constraints are consistent with the evolution equations. Okay? But now let's think about this from a numerical perspective. From a numerical perspective, that means if doing the evolution, let's say because of our numerical error, we've built up, sorry? Yes, go ahead.
The computation is possible.
So I say that again. Yeah.
Here,
yeah.
From that term,
yeah.
Is commutation possible in the D operator section?
Oh, in the D operator. Okay, so I am allowed to do that because I'm doing this in flat space, right? In general, there would be Ricci tensors that would appear, okay? But basically in flat space, those Riemann tensors, I'm sorry, okay? Those Riemann tensors are zero, so they disappear. So I don't need to worry about it, right? So for example, we could do this exercise in Cartesian coordinates. Then all the D's would just be partial derivatives. And then you would believe me that I can just interchange the partial derivatives. I can take them in either order. Okay? Yeah. Makes sense? Okay, good. Yeah. And okay. All good? Okay. So now let's basically, again, think about what happens if we build up a numerical error, maybe in the course of a numerical simulation. Then what this tells us that error will not go away. It will just hang around. Okay? So basically that error will just build up if you want to. Okay? Okay, so, but a non-zero, the constraint violation C will persist. You agree? Let me show you how we could construct a reformulation of Maxwell's equations that would allow constraint violations to go away. And it turns out that's pretty simple. I can do that in a few little steps. Okay? So let's consider the following reformulation. In the first step, I introduce a new variable. I'll call it gamma, and the reason for that will become clear pretty soon. And I define this gamma as the divergence of A. Okay? And then basically I consider this gamma a new independent variable. What that means is I don't compute gamma from A at each time. Instead, I start with certain values for gamma, and now I want to evolve gamma with its own evolution equation. That means we now have to derive an evolution equation for gamma, and we can do this by just using our existing equation. So let's figure out what that is. We have a new evolution equation for our new variable. How can we do that? I compute the partial derivative of gamma. That is the same as di of partial t ai, right? Now I use the equation for ai. I insert that, and then I get minus the divergence of E, okay, minus di phi. Okay. Now, remember earlier today, I told you we can do two things in coming up with a reformulation. We can introduce a new variable. That's what we just did. We can also add the constraints. And that's what I'll do now. I'll use the constraints to replace the divergence of E with the charge density. Okay, so this is therefore, okay, so at this point, I will add the constraint, which was C equals di ei minus 4 pi rho equals 0. If I add this, then I see that these two terms cancel, and I get a 4 pi rho. So then I have partial t gamma equals minus di phi minus 4 pi rho. Okay. So this is our new evolution equation for gamma. We still have these two evolution equations, but what I'll now do is I'll replace our term of concern with the derivative, the gradient of our new variable gamma. So our new evolution equations for E and A are now the following. Also, we now have partial TAI equals minus EI minus DI phi. This is unchanged. And we have partial TEI equals minus DJ AI plus DI gamma minus 4 pi JI. Okay. Now, at least hand-wavingly, you could say, now the highest derivatives on the right-hand side are now reduced to only this term, which is just a Laplace operator. That's kind of similar to the scalar field equation. Again, that seems like good news. Okay. Okay. All right. So basically, the bottom line is that what we've done here, we've absorbed the mixed second derivatives. If you want, okay, the term of concern has now been replaced by this one. All right. What we can now do, okay, my claim, remember earlier, was that when we use a reformulation, what changes is the behavior of the error. For the original set of equations, we evaluated the error by looking at the time derivative of C. So now we could revisit the same equation, the same argument, and we would notice that actually C no longer satisfies this equation. This partial TC is no longer 0. Instead, I'll ask you in the tutorial to prove that C now satisfies a wave equation. Okay, so you can show that C now satisfies a wave equation. Okay. I.e., you can show, and again, you'll do that on the tutorial, that C now satisfies this equation equals 0. Okay. That means C now behaves very differently. Okay. Before, we argued in our original formulation, if C is non-zero during the evolution, it will just stick around. It won't go anywhere because its time derivative is 0. Now, if we build up some error, then what happens to this error is it satisfies a wave equation. What do waves like to do? They like to propagate. Okay? So given suitable boundary conditions, these constraint violations will just propagate off the numerical grid and they will disappear. You can actually check in simple implementations that as a consequence of that, the constraint violations will decrease exponentially if you use this reformulation, not with the original formulation, but with this one it does. Okay? So the key point here is the following. Okay? So that the constraint violations propagate. Okay. And in fact, they propagate at the speed of light, which is 1 in our units, right? And that means, so they satisfy wave equation, they propagate, okay? And then the key point that we take away from this exercise is the following. The analytical solutions for which C is 0 are exactly the same in the two systems. Okay? So analytical solutions for which C equals 0 are identical. But for numerical solutions that always have some error, which we might measure by C, okay? For numerical solutions, for which C is different from 0, okay? The choice of the formulation will affect the behavior of numerical error. Okay? And therefore, different formulations will have different stability properties. It is possible that in one formulation, the numerical error becomes larger and larger until the code crashes, whereas in other formulations, the numerical error may remain bounded, it may even decrease, it behaves differently. Okay? So basically, therefore, we encounter different stability properties. Okay. Make sense? So really, I have not told you whether this original formulation of ENM or this reformulation, which one would be stable or unstable. In fact, both of them are linear systems, both of them will be stable. The only thing that I've demonstrated to you is that if you have a constraint violation in either one of the two systems, then that constraint violation will behave differently, okay, in the two systems. Okay, that's all this example shows you. But what that means is that when you use a reformulation of the equation, you should expect the numerical error to behave differently. And then it's intuitive that in some cases that may lead to stable evolution, whereas in other cases it may lead to unstable evolution. Okay, all right. Now, so that was in ENM. Oh, and by the way, basically in the tutorial today, yesterday I think you played with a Python script to, just 1 second, okay? You played with a Python script to solve the constraint equations, right? Puncture.py. Today, you should already have a Python script that solves these Maxwell's equations, and you can, with a switch, you can evolve it either with the original formulation or with the new formulation, and you can see for yourself how the constraint behaves, and you can explore all of these properties. Okay? All right, you had a question. So is the definition of gamma what?
Another constraint that you should ensure holds.
Okay, so why did I choose to define gamma in that way?
You chose that definition, that's fine.
Yeah.
But as you evolve it, it may happen that the evolution equation itself leads to error.
That's absolutely true. So, okay, just to repeat the question, basically we defined gamma as the divergence of A, but I also told you we do not evaluate this equation, or we don't compute gamma doing the evolution from this equation. Instead, we compute gamma doing the evolution from this evolution equation. Okay? And what that means, of course, is that even though maybe we computed gamma originally at t equals 0 initially from this, at later times, this equation will no longer hold. Okay? What that means is that this equation actually now serves as a new constraint equation. So in this new system, you effectively have two constraints. You have one constraint, which is our original, well, the Gauss's law, divergence of E equals 4 pi rho. Okay, but the other constraint now is this. So basically, we have a new constraint that we can also use, for example, as a diagnostic to monitor a numerical error. You're absolutely right. Yeah. Okay.
If we have to care about that blowing up.
So we would, okay, if that blew up, that would also be a bad sign. Okay, so we could also look at the constraint violation of that. Okay, but that's a separate thing. You go for it. You should. Okay, yeah. Okay, that was ENM. Now we'll apply the same technique to GR. We'll talk about what's going on in GR, just as we did all the other times when we invoked these analogies. Okay? So let's see, what can I erase here? Maybe I'll start over on the left-hand side. Okay, so what we've taken away from this is that the core of the issue are those mixed second derivatives that we encounter in the evolution equation. In GR, as we said before, those mixed second derivatives appear in the Ricci tensor. That's where they're hidden. So let's talk about that. In GR, okay? So at the core of the issue is the Ricci tensor. And as I said a minute ago, we can write down the Ricci tensor in basically at least three different ways. I'm familiar with the three different ways of writing it down. You can look at the handout that I gave you with the results. And if you look at equation 8 on that sheet, you see that one way of writing it is in terms of the second derivatives of the metric. And then it looks something like this: GCD times partial C, partial D, GAB. And then we have permutations of these second derivatives. So there's one term that is partial A, partial B, G, C, D. And then we have a minus partial C, partial A, G, B, D, and a minus partial B, partial D, G, A, C. And then we have terms that are quadratic in the Christoffel symbols. Okay? This is, maybe you've seen this before from a general relativity class. If not, trust me, or just think about the analogy with ENM, where you also have these second mixed derivatives. The first term looks like a friend to ours, right? Because it is the contraction over the second derivatives on each component of GAB. So this is not precisely a Laplace operator because these are not covariant derivatives, they're partial derivatives, but it acts like one. Okay, so this is kind of, sort of like a wave operator. In 4D, this would be like a wave operator acting on GAB. Okay, so kind of, sort of, right? You with me? Similar to how in ENM we identified the first second derivatives of A as our friend, right? The term that we liked. And it was the other permutations that were the terms of concern. And it's the same thing here. Okay, so we have these three terms which now spoil the wave behavior or wave characterization of this operator. So they spoil the wave, maybe I call it characterization. Okay? And our mathematician friends would say, whoa, careful. Okay, that may cause problems, and indeed it does. Okay, but here's the beautiful thing: we can follow the exact same steps as in ENM to deal with these terms. Okay, so it turns out we can absorb all of these three terms in terms of a new variable, which is a contraction, basically the divergence of our original variable. Okay, so but as in ENM, we can absorb the terms of concern in a new term, which is a G, C, and now the symmetrized version of the partial VA of gamma C, okay? And basically, this was equation 8 on the result sheet, you should now look at equation 9 and you'll see that form written down, okay? See equation 9 on the results. Okay, I don't think I need to copy it down here. Okay, but what I do need to do is I need to tell you what these gammas are. Okay, where or with gamma C is defined as the contraction dE of the Christoffel symbols. And if you've taken a general relativity course, then maybe you remember that basically there is a neat identity for evaluating these terms, and because I can write them as 1 over the square root of the magnitude of the determinant of the metric times partial A of same determinant, GAC. Okay? So we can express this as partial derivatives of G. Okay? And, with a little bit of goodwill, you realize that, this is just a divergence of the metric. So in fact, remember what we did in ENM? We defined a gamma as the divergence of A. Now you realize this gamma is the exact same thing. It's the divergence of our fundamental quantity G. Okay, just one index more. And here throw in a few determinants for good measure. Okay, fine. Okay. But the structure is exactly the same. And then it turns out that all of these three terms become just a partial derivative of this gamma, just like in ENM. Okay? So basically compare this. Compare with gamma equals DI AI. Okay? It's the same idea. Okay? All right. So now this is at the core of the matter. And actually there are basically two major formulations that people use in numerical relativity these days. One formulation will play a very big role next week at this workshop. That is the generalized harmonic formulation. And the generalized harmonic formulation uses this idea directly in 4D, okay, in 4 dimensions. So in the generalized harmonic formulation, basically here the idea is you actually solve the 4D equations. You still have to solve constraints, just like we did yesterday, okay? But then you solve 4D equations. You use this idea to write basically Einstein's equations as a wave equation for the metric, okay? But, and you can do that by absorbing basically all these mixed terms into derivatives of the gammas, okay? Now, where does the gauge freedom come from? You can now impose a gauge by making certain choices for these gammas. Okay? So these are now 4-dimensional gammas, and you set them equal to some gauge source functions. Okay? So these are chosen gauge source functions. One special case would be if we choose all the ages to be 0, then it means all these gammas would be 0. That means that all of these 3 terms go away. And in fact, we have only a wave equation for G, okay, plus non-linear terms. Those coordinates are called harmonic coordinates, okay? So basically, as course, for HA equals 0, we call that harmonic coordinates. Okay? And in fact, a lot of the mathematical studies that were done in GR were done using these harmonic coordinates precisely because in that case, Einstein's equations is reduced to essentially nonlinear wave equations. Okay? And you can see why this formulation is called generalized harmonic formulation, because you generalize the harmonic coordinates by allowing H to be non-zero. You make other choices, okay? That's how you impose the gauge here. Yeah, anyway, I'll just leave it at that. And in fact, basically, it was with this formulation that Franz Pretorius was able to perform the very first successful simulations of black hole binary mergers. Okay, so the first successful simulations of binary black hole mergers were done with this formulation by Pretorius, Franz Pretorius in 2005. Okay, that was a huge breakthrough. Now, he used this formulation. I should also say that other people had contributed to this formulation, absolutely. In particular, Helmut Friedrich did a lot of work with this, but then other people had made suggestions for how to damp constraints. David Garfinkel, I believe Carsten Gundlach, and other people. Okay, so lots of people contributed to this, but Franz Pretorius really did these remarkable simulations in 2005, where he was able to simulate the merger of black holes for the first time. Now, this formulation also is the basis of the spec code, or the Spectre code, which I believe you will work with next week. Okay, so this is the basis of the spec code. Okay, so that you will hear a lot more about that next week. That is one formulation that uses basically these ideas, right, of absorbing these mixed derivatives in a new variable. Another formulation that is very commonly used is what people refer to as the BSSN formulation. Okay? So let's talk about that. Of course, it's kind of dear to my heart, as you may understand. Okay, so I'm happy to talk about that. Okay, so BSSN, and this was originally actually worked on by Nakamura and collaborators in the late 80s. Then it was made famous by Shibata and Nakamura. In 1995. And then Stu Shapiro and I kind of we added some final touches, if you want to, in 1998, and then people called it BSSN. Now, where do these equations come from? Actually, now that we've gone through the analogy with ENM, it turns out you can follow the exact same footsteps. Okay? So basically, when we talked about the reformulation of ENM, what did we start with? Well, we started with Maxwell's equations, and similarly here, you can start with ADM. Now, before you do anything else, it turns out to use some of the techniques that we discussed yesterday. Remember, one trick that we used yesterday in solving the constraint equations is we introduced a conformal transformation. And that turns out to be useful here too. So we introduce a conformal transformation so that we write gamma ij as psi to the 4 times gamma bar ij, as we did yesterday, except that it's common, okay, following the original work by Nakamura and Shibata, to write the conformal factor rather as a psi itself as an e to the phi, okay, but it's the very same idea. Okay? Now, that by itself is not unique. Basically, we could make different choices. If we make a different choice for psi, we make a different choice for gamma bar, right? So there's no uniqueness here. But so we can impose an extra condition. So for example, in Cartesian coordinates, it's a very natural choice would be to choose the conformal factor in such a way that the determinant of the conformity related metric is 1. And actually that motivates using this conformal transformation at all, as we'll see in a minute why that is useful. Okay, so let's keep that in mind. Yes, was there a question? Yes.
So psi equals h to phi is chosen to make sure that psi is always positive.
So say it again. What is
This is taken to assure that psi is always positive.
Is psi always positive? So I'm hesitating a little bit because I don't want to write a blank check, okay? I mean, you could imagine maybe so doing an evolution, certainly you would want that, okay? Can I guarantee that that will always be the case no matter what the evolution is? I'm not sure. I mean, things could go wrong, okay? But certainly you would absolutely want it to be positive, definitely, yes. Yeah.
So in this case, phi can take any value, but no matter what, psi will remain positive.
That's right, yeah. Yes, exactly. You want psi to be positive, and actually this writing it this will ensure that. That's true. Yeah. Yeah. You had a question too, right? Yeah.
But in our ADM equations, we use alpha like labs function.
Yes, you're absolutely right. So basically in this context, and we'll come back to this in a minute, we'll use the lapse and the shift to impose constraints. In the generalized harmonic formulation, actually, you do not work with the lapse and the shift, okay? So basically, it's a fourfold coordinate freedom. In basically ADM formalism and BSSN and other 3+1 decompositions, you impose the fourfold coordinate freedom by making one choice for the lapse and 3 for the shift, right? The shift being a spatial vector, okay? Here, you choose these 4 functions H, which give you the 4 components of these gammas, okay? And basically, you don't work with the lapse and the shift there. Actually, one comment that what I meant to make is one thing that I like about these formulations is that you have a geometric interpretation of what the lapse and the shift do. That is on Tuesday we talked about that, right? Basically, we talked about what the lapse and the shift do. So we have a geometric interpretation for how we impose our coordinates. In these formulations, the geometric interpretation of what these gauge source functions do is a little bit more murky, I would argue. Okay, so it's a little bit less clear what exactly these coordinates will do. Okay, but thank you for asking that. You're absolutely right. Basically, there's no lapse and shift in the generalized harmonic formulation. Okay, or at least not a priori. You can basically fit it back in and then work with it. Yeah. Okay. Good. All right, okay. So now we have this conformal transformation. What are we doing next here? Okay. Once we have done the conformal transformation, we could do what we did yesterday. We could basically write things again all the geometric objects we can write in terms of the conformal geometry or the conformal metric, right? So yesterday, for example, we wrote, and you did this in the tutorial also, we wrote the spatial Christoffel symbol in terms of the conformally related spatial Christoffel symbol plus derivatives of the conformal factor, right? You showed how you can do that. Likewise, we can write the Ricci tensor, the spatial Ricci tensor, the physical spatial Ricci tensor as the conformal spatial Ricci tensor plus derivatives of the conformal factor. Remember that? Now, basically, we can do the same thing. Once we've done this conformal transformation, I'll again write the Ricci tensor as a sum of 2 parts. One is the conformally related Ricci tensor, which has all the second derivatives of the conformal metric, plus the term that contains all the derivatives of the conformal factor. Okay, so we then have the spatial physical Ricci tensor now splits into 2 terms, the conformally related cousin plus the term that has all the derivatives of phi, which I denote by writing r to r phi. Okay, so this contains derivatives of phi. Okay, and now basically we are worried about this term because this term contains the mixed second derivatives of the conformally related metric. And it is in this term that we now use this trick where we write those mixed second derivatives in terms of derivatives of new gammas, which we define in exactly the same way, just spatial and with bars. Okay, so basically we write Rij in terms of gamma I equals gamma bar Lm, gamma I Lm, and that's the same as this. Basically, using this identity, I can write that as 1 over the determinant of the conformally related metric times partial j square root of gamma bar times gamma bar ij. Okay, you with me? Good. Now let's remember what we said here. We have some freedom on how to choose this. In Cartesian coordinates, for example, we could choose the determinant of the conformally related metric to be 1. You did not object to that, right? Why is that a good choice? Because if we go here, that would really simplify this expression, right? If these determinants are 1, then this is really just a divergence of the conformally related metric. That's pretty nice, isn't it? Right? Okay. All right. Now, what we still need to do is derive an evolution equation for the gammas. Okay. So we treat gamma bar I as new independent variables. Okay. So rather than imposing a condition on the gamma bars ij, I want to, this comes back to your question. Okay, you ask about the shift terms, for example. We could impose a condition on this, but I'm not going to do that. Instead, I'll derive an evolution equation for it. Okay, and basically, once we then have the evolution equation, we can impose the gauge still with a shift. So we still have the freedom to impose the spatial coordinates with a shift, and we still have the lapse for the time coordinates. So we treat this as an independent variable. That means we derive an evolution equation as in ENN. How did we do that? Well, we started with the time derivative of gamma. Okay. Then we inserted the definition of gamma. If gamma bar is 1, then actually this is just a divergence of the metric. Okay, so this would now be a partial d partial I of that. Then we can commute the partial d partial I. Then we can use the evolution equation for gamma to get rid of that, just like in ENN. And then there was one more step that we did in ENN. Does somebody remember? We added the constraints, right? And look how that, let's just picture what happens. So basically, I want to derive an evolution equation for the capital gammas. So then I have a time derivative of this. Let's say these determinants are 1. Then I have a time derivative of this. I commute the time derivatives. Then I have a partial I, partial t of gamma. The time derivative of gamma I can express in terms of what? That was the extrinsic curvature. Okay, so I can express the time derivative of gamma of the metric as the extrinsic curvature. Now I have the divergence of the extrinsic curvature, right? You see that? And where else do you see the divergence of the extrinsic curvature? In the momentum constraint. So now we can use the momentum constraint to get rid of that term. And you notice, enjoy this, okay? Isn't this lovely? That's exactly what we did in ENN. Okay, we can do exactly the same steps. Okay, all right. So, and once we have done that, we are done. Okay? Then we have basically derived the BSSN equations. Okay, and again, basically, there's no need to go through each step and check every index. Basically, what we've discussed are basically all the ingredients, the conceptual ingredients that you need for that. Okay? And then it's really a beautiful thing if you basically integrate these BSSN equations, then those are much better behaved than the original ADM equations, and people have used them extremely successfully for black holes, but also neutron stars and all kinds of other things. Okay? Sounds good? Of course, the skeptics among you might argue, how would we know? Because there's still something that we haven't talked about. We still need to discuss something. And that is, you've been smiling so knowingly. No. We still need to talk about, well, what choices are we going to make for the labs in the shift? Right, so we still have a little bit of time, right? Yes, plenty of time, excellent. So let's talk about what choices can we make for the labs in the shift? Okay, so let's talk about slicing and gauge conditions. So in other words, basically what I mean by that is we need choices for the Laps function and the shift vector beta, alpha and beta. Okay. Now, when we play with choices, what choice should we always try first? The easiest, probably, right? What would be the easiest here? Any objections against alpha equals 1, beta equals 0? Let's talk about what that would do. Okay, so why not alpha equals 1 and beta I equals 0? Okay. Now remember, I think on Tuesday, we introduced the time vector, okay, which was tangent to word lines of coordinate observers. Remember that? TA, we called it TA, and TA was alpha times NA plus beta A, okay? You agree? Okay, or look, I don't expect you to memorize this, okay? But you can look it up in your notes and probably you would find it and then you'd be satisfied, okay? And we interpreted, remember we interpreted N as basically that was the normal on each slice. We discussed N as the forward velocity of a normal observer, whereas the T was tangent to a coordinate observer, i.e. an observer whose word line connects points on each slice that have the same spatial coordinates. Okay. Now, if alpha equals 1, if beta equals 0, then you agree that those two are actually the same. Okay. So that means that coordinate observers are now the same as normal observers. That means that each spatial coordinate will be the same along the word line of a normal observer. All right. So the coordinate observer is the same as a normal observer. Okay. Also, let's remember, how do we define the acceleration of the normal observer? Let's call it AA. Does anybody remember? That was? So that's right. So there's an N, let's call it B, nabla B, and A, right? You agree? Now, did you do this exercise in the tutorial that allowed us to rewrite that? That was, okay. So that involved several steps, but by the end of the day, you found that this was the same as the spatial gradient of the logarithm of alpha. You agree? Okay. What is that if we're choosing alpha equals 1? 0, right? So this is 0. So that means that what kind of a word line does this normal observer follow? A geodesic. So our normal observers are freely falling but the normal observers are the same as the coordinate observers. That means coordinate observers are freely falling. Okay? So now imagine we have a space-time where maybe there's a little blob of matter, or maybe just some gravitational wave, something gravitates, okay? That will exert gravitational forces, right? Which really, we don't talk about forces in GR, but you get the idea. So what will, if there's some gravitating something rather here, and we have an observer here, what will this observer do? If it follows a geodesic, it will fall in. And so does this observer and all of them, and they will cross. And when coordinate lines cross, we generally don't consider that good news. That means our coordinate system just went bad, okay? So basically what you see is generically, geodesic coordinates are a terrible idea because it automatically leads to coordinate lines crossing. Almost automatically, okay? There's some cases where that doesn't happen, okay? And in fact, in those cases, these coordinates are very familiar. Anybody know what I'm talking about? Sorry? Well, I mean, okay, in empty spaces, but so I agree, okay? But even in non-empty spaces, basically, if the observers are flying apart, okay? In cosmology, you actually use these coordinates all the time in cosmology, okay? But there, basically, you follow basically an expanding universe, and basically, then this is okay. Basically, they will not cross because they're flying apart, okay? But if you let that, but in basically most applications that we have in mind, these coordinates basically don't work well. Okay, so basically, we see that in the coordinate observers follow geodesics. Okay, and therefore we call this choice geodesic slicing. This is called geodesic slicing. Okay, all right. But we notice that because coordinate observers follow geodesics, they will be focused. Any gravitational source will focus these observers, so it leads to a focusing of coordinate world lines. Okay. And that leads to coordinate singularities. It will make your code crash in a finite time. And in fact, in the tutorial, I'll ask you to even estimate the maximum time that your code could possibly survive if you use these coordinates, okay, under certain circumstances. So the code will crash. So that answers our question, why not use the simplest choice possible? Because it's not a good choice. We have to come up with something else. Many people have used different choices. One choice that was very common a little bit in the past was maximal slicing, where you set the mean curvature to 0, but it involves solving an elliptic equation. Another choice that was considered by many people, it was harmonic slicing, okay, as alternative. You could try harmonic slicing, by which we mean partial t, alpha, equals minus alpha squared k, okay? And in fact, this is a special case of the coordinates that we impose in the context of the generalized harmonic formulation, where basically this corresponds to setting the t component of our gauge source functions to 0. So that is a case where there's an equivalence or there's a relationship. Okay, okay, we could also generalize this. Okay, there was a group of people, Bona and Mussel and collaborators, okay, who suggested generalizing by inserting an extra function that depends on alpha only into this equation. Okay, so where we still have to choose this. You still need to choose. So this was suggested, this family of slicing conditions was suggested by Bona and Mussel and collaborators. et al. Okay, 1995. The most common choice for this f of alpha is called 2 over alpha. Okay, so the most common choice is f of alpha equals 2 divided by alpha. So our condition then becomes partial t alpha equals minus 2 alpha k. Okay, and it turns out if you combine this with the evolution equation for the mean curvature, you can show that under certain conditions, this is then equivalent to having labs equal to be 1 plus the natural logarithm of the determinant of the spatial metric. Okay? And therefore, this condition is called 1 plus log slicing. Okay? Because of this identification 1 plus log. Okay. All right. So basically, people just played with different slicing conditions, and this was something that looked promising for a number of different reasons. It had some properties that looked very promising. People played with it, also generalized it. In fact, basically, this is a little bit awkward because this is the partial time derivative in order to basically make it more geometrically meaningful. Maybe we want the time derivative along the normal vector rather than the coordinate observer. So basically there was one more generalization, which I refer to as an advective version, where we just add to this an extra shift term. So rather than only having the partial time derivative on the left-hand side, we add a beta I partial I of alpha, which then you can see is the same as alpha times NA partial A alpha. So this is the derivative along the normal vector. And on the right-hand side, we leave minus alpha squared f of alpha times k. Okay? So this is a slicing condition that people played with and experimented with. That determines the lapse. Of course, we still have to determine the shift. Okay, but basically, I will skip a few details. I will just tell you that a shift that people played around with a shift choice that leaves, basically aims at leaving these gamma bars, these new connection functions, so to speak, or they were called connection functions, basically leaves them more or less unchanged. Okay, so that's called a gamma driver. So we can combine this with a so-called gamma driver condition for the shift. Okay. And then combined, these coordinate conditions are now often called moving puncture coordinate conditions, or sometimes called the standard gauge, because there's so many people use them, they've been so successful. Okay, so this is the moving puncture. Whoops. Gauge. It turns out this particular combination has been extremely successful for simulations of black holes and neutron stars. Okay, but the first breakthrough actually was used for neutron stars even early on. But then, basically, when people really tried to simulate black hole binaries, it turns out shortly after the breakthrough by Franz Pretorius, there were two groups independently who used the BSSN formulation using this moving puncture gauge, and also were able to complete successful black hole simulations. Okay, so this was very successful, has been very successful for simulations of black holes. And in particular, there was kind of a miracle, whereas Franz Pretorius in his simulations needed to so-called excise the black hole. So basically, he moved the grid points close to the black hole away from the grid so that the singularities inside the black hole don't spoil the evolution. You could worry about saying, well, how can you do that? Well, they're inside the black hole. They're inside the horizon. So, according to the properties of a black hole, any information from inside the horizon cannot propagate outwards. So you're supposing that should be possible, except that the details are often very complicated. Okay? Now you have trouble reading something, is that right? Oh, advective is, I'm sorry, but so the advective version, it just refers to this extra term, the shift term that acts like an advective term that advects this condition along the normal. Yeah. So unlike in the simulations by Franz Pretorius, if you use this gauge, it turned out you did not even need to excise the black hole. It seems to work right out of the box. It is remarkable. Okay, so basically, let's write this down, and then we'll talk briefly about why that is. There was no excision of the black hole needed. This was discovered basically by two groups almost simultaneously. One was by Manuela Campanelli and collaborators in 2006, and the other was by John Baker and Joan Centrella and collaborators also in 2006. These two papers appeared in PRL right next to each other, okay? This left a miracle. Why is it that with these coordinates, the singularities inside a black hole do not spoil the numerical evolution, okay? We talked about black holes briefly on Monday. We didn't take much time to talk about the nature of singularities. Remember, there's a coordinate singularity on the event horizon, but that is harmless. In fact, even in the tutorials, you saw that we can introduce different coordinate systems where that singularity completely goes away. Okay? However, there's also a curvature singularity at the areal radius big R equals 0, where the curvature goes to infinity. That's a non-negotiable singularity, and certainly you would expect that singularity to spoil any numerical evolution because computers don't like infinities very much, okay? So how can it be that these coordinates allow you to essentially get away with murder? Okay, you don't need to worry about those singularities. And basically that was clarified by a group in Jena, by Mark Hanam, Sascha Husa, Bernd Brickman, Neil Omudu, and other people, who basically did precisely what you should do if posed with this mystery. You should apply these coordinates to a simple spacetime that we understand very well, to the Schwarzschild spacetime, and explore what happens in the Schwarzschild spacetime when you have these solutions, okay? And what happens for Schwarzschild is this. So for Schwarzschild, okay? Basically what happens is that when you start with, let's say, the isotropic Schwarzschild initial data that we've encountered several times. On Monday, we talked about it. You talked about it on the tutorial, or you discussed it in the tutorial. Yesterday, we talked about them in the context of the initial data. We could use those as initial data. You evolve them with these moving puncture gauge, and then you explore what happens to the spatial geometry. Okay? One way to explore spatial geometry is to draw so-called embedding diagrams that kind of picture the geometry of a spatial slice. If you let basically this evolution settle down for Schwarzschild, and then check what geometry do we settle down to, if we do that by drawing an embedding diagram, we would come up with a diagram that looks something like this. Okay, so this is the infinity, but then basically it looks something like that. Okay, so it asymptotes to a cylinder. And because with a little bit imagination and maybe better drawing skills, this looks like a trumpet, people refer to this as a trumpet geometry. Okay, so basically in this case, the slices settle down to a so-called trumpet geometry. Now, in this diagram, basically the radius measures the area radius. And what you notice is that basically these slices never come to an area radius of 0. You see what I mean by that? In fact, on Monday, on the tutorial, I asked you to consider an analytical version of this. Remember that? And it's basically for this analytical trumpet solution, you found precisely that. You introduced a new isotropic radius, little r, but you notice that as you let the little r go to 0, the aerial radius r remained positive. Remember that? that meant that that slice does not go all the way to the curvature singularity. It avoids the coordinate singularity. And I'm the curvature singularity. I should be careful. Should I say that one more time, just because I messed up myself? Basically, these slices do not go to an aero radius of 0. They stop before. They never reach big R equals 0. And that means they never reach the curvature singularity at the center of the black hole. You could argue that is kind of like excision. We've excised the inner region of the black hole, except we didn't do it by hand. We let the coordinates do the job for us, okay? Much nicer. We delegated. Perfect, okay? Now you could still argue, but wait, fine. So we removed the curvature singularity, but you derived, on Monday, in the tutorial, you derived the conformal factor for that. And you know, if you can look at your notes, okay? If you look at your notes, you realize that the conformal factor still goes to infinity there. It went with 1 over the square root of R. So there's still a coordinate singularity. So you could ask, but great, so how does that help? Because there's still a coordinate singularity. And it's true, that coordinate singularity will happen all the way down. Okay? But here's the other beautiful property of these slices. You also found on Monday that any point at a finite r at greater than 0, even epsilon, is an infinite distance away from the coordinate singularity at r equals 0. Again, because of the special property of the conformal factor going with 1 over the square root of r. That is at the core of these trumpet geometries. That means that any grid point that is anywhere here is an infinite difference, proper distance away from the coordinate singularity all the way down, okay? So that means that essentially, yes, there will be some numerical effects that give you some error there, but nevertheless, basically those errors, it won't propagate, it will stay contained to those areas. And that, in a nutshell, gives you some insight as to why it is that basically you get away with murder and you can put these black holes in the grid and the grid will be fine, the coordinates code will be fine. Yes, go ahead.
So this means that in a numerical implementation, the singularity is never in the grid.
That's right. That's right. So you will have a grid that covers all space, but basically the radius that you're using in your grid is the isotropic radius little r if you want to. And there's no value of little r that corresponds to big R equals 0. And therefore the curvature singularity is not on your grid. Okay? Yeah.
So this also means that when we do binary merge simulation,
Yeah.
so we also need to make sure that the center of either of the black holes should not coincide with any of the group holes.
Probably. Okay, so why do I say probably? You're right. So for example, basically you could say, well, but the conformal factor still goes with 1 over r. So let's say if I have a grid point that happens to be at exactly the same place, then that point will go to infinity and that should kill my simulation, okay? Now, how could we avoid that? Okay, one would be, okay, maybe there's certain symmetries. Let's say basically that the binary is in the equatorial plane. Maybe we use a cell-centered grid. So in that case, the singularity will never be at that point. Or you could do something else. So for example, some of these groups, like Manuela Campanelli's group, they rather than using the conformal factor as a variable, they use the inverse of the conformal factor as a variable. So when the conformal factor goes to infinity, the inverse goes to 0, and it remains harmless at that point. So there's different ways of dealing with that issue. But you're absolutely right, you have to think about it, okay? Yeah. Mm-hmm. Okay, let me wrap up this story here. So there's basically this settles down to a trumpet geometry. Basically, that means we avoid. Yeah. Okay. We avoid the space-time curvature singularity. That means there's no need for excision because it's already done for us. Okay, the coordinates take care of the excision. Okay, and basically also all spatial grid points are at infinite proper distance from the coordinate singularity. At r equals 0. Okay, and all of this was basically shown or discovered by basically the Jena group around 2007. There are several papers with Sascha Husa and Neil Mudu and other people. Okay, so basically that explains why basically these trumpet geometries allow you to do simulations of black holes without even having to really worry about the black holes, which I think is just a really neat property. I like that a lot. Okay. Basically, after the fact, we understood this much better, of course. Okay. One thing that I was very pleased with is that we can actually write these trumpet geometries analytically, okay, and explore all these properties analytically with pencil and paper. That's exactly what you did on Monday. Okay, so on Monday already I gave you this example in the tutorial where you can explore these properties and you can see how this works. Okay, and basically you've returned to that problem multiple times through the week. You will do that one more time today to see how you could get such a trumpet geometry, this analytical trumpet geometry, by imposing a slicing condition like this just for one particular choice of this function f. Okay? All right, so this explains why these slicing conditions are very successful for black holes. I'll just add to this, they have also been extremely successful for other space, not all spacetimes, but for many others, including for neutron star spacetimes like the ones that Ken Takeuchi told us about. Okay, so this has also been has led to great success for neutron star. Oops. There are spacetimes. And that brings me to the end of my lectures here. So before I say goodbye, though, I would like to say that I've really enjoyed talking to you all week. It's been really a great pleasure to be here. So again, I would like to thank the organizer again for inviting me to come to this really remarkable and impressive and beautiful place. It's been great to meet you all. And I will just add, I've been very impressed with you because you had to listen to me for hours and hours and hours, and you're still awake. How did you do that? Okay, I'm impressed. You had lots of great questions. And I'm impressed when I walked by at 6 p.m., you were all still in here doing the tutorial. So it's rare that I've seen such a motivated and dedicated group of students. So I'm very impressed. Again, it's been great to meet you all. Okay. So, one quick thing I've received several requests for LinkedIn connections. I'm not a social media type of person. I have one social media account, that's the LinkedIn account, which I immediately regretted opening it. So I forgot my password. I'll try to so once I've found it again, I will accept your request. But please be patient. That you won't learn much from that. Okay. I'll leave it at that. Again, it's been great to be here. It's been great to meet you all. So thank you all, and I hope we meet sometime again. You had a question, I believe, right?
So there are more different possibilities of formulations.
Absolutely, they are. Okay, so basically, people have I told you about this, what people refer to as the BSN formulation. There are other formulations. So the question is, are there other reformulations of those? And absolutely, there are. And in particular, there is a so-called Z4 formalism. Okay, that was developed by Bona, and then originally, but then basically by other people like David Tildich and other groups who basically Sebastian Benuzzi and other people who basically reformulated this again. And some of those actually have advantages, in particular for neutron star spacetimes, where they lead to significant reduction in the constraint violations. So yes, absolutely, there are further reformulations of those equations, but the ingredients are kind of similar. Yeah.
So will there be a position where we will be able to say that this is the best possible reformulation?
Oh, I don't know. I mean, yeah.
Crystal Zegers coordinates are best.
Right. I mean, it's entirely possible that different formulations have better properties for different applications, just like some coordinate conditions might be better for one application and others might be better for others. And so there are many different applications we've talked. I mean, mostly I had in my discussions here, I had in mind black hole evolutions, but we could talk about neutron star evolutions. But then people use this for other things too. You know, maybe. You know, I discussed in a seminar critical collapse simulations this week. So that's a different class of simulations. People use this formalism for cosmological simulations, right? So basically, there's many different applications, and there might be different versions where maybe, you know, different terms are more or less important. And so I'm not sure there will be one gold standard, but I might be wrong about that too. Yeah. Thank you. Yeah.
So I have 2 questions. So maybe I missed it. So what are gamma drivers?
Okay, so gamma drivers, right. So I mean, I kind of ran out of time, so I didn't want to spend too much time on that. Basically, this is a shift condition that was developed by Miguel Alcubierre and Bernd Brigman and collaborators of theirs. Okay, but the idea is that you write, okay, what would we have to do in order, if we wanted to say, actually, maybe it's a good idea. Basically, okay, the general philosophy is when you do a numerical simulation, then presumably your numerical errors are smallest if your variables evolve the least. Okay, so if you have variables that don't evolve at all, then presumably you can do that very accurately. So one of the variables, the new variable, these gammas, which are called the connection functions or the conformal connection functions, basically they're just certain variables, and you could say, well, maybe it's a good idea to make the evolution of those variables as small as possible. So you could check, and if basically we could formally set the time derivative of those variables to 0, that would give us a very complicated equation for the shift. And it's basically an elliptic equation, I believe, okay? And basically that will be complicated to solve during the evolution and expensive. So you don't want to do that. So then you say, okay, maybe I don't want to solve that equation precisely, but I don't need to solve it precisely. You know, maybe I can just basically solve it in approximately, but in a cheaper way, okay? And basically that's essentially what this gamma driver is. So basically over long times, this driver derives a variable to a certain state or something, and that's what this does, okay?
It is more like a constraint equation which forces betas to approach.
That's right. It basically, the idea is that it would force the gammas to settle down to certain constant values. Okay?
By gamma, you mean contracted wisdom?
The contracted, that's right. So the gamma bars, right? So, which I'm not even sure, I should have said that. Basically, remember I introduced these variables gamma I. These are called the conformal connection functions. Okay, and it's basically, this is, in the gamma driver, you come up with a condition that reduces, let's say, the time evolution of these variables, okay? And that has been very successful too. There's different versions of those around, okay? And different versions are better for some applications or others. Yeah. Okay.
Another question is, in
Yeah.
1 plus log pricing,
Yeah.
are they assuming that in the infinite future alpha goes to 1? So why this one constant after time integration?
Okay, so you're asking where does this 1 come from?
Yeah.
From the initial data. So basically, how do you derive this? You use the, actually, I think I said this wrong in my class, actually. So you can in the tutorial, I asked you to derive a time evolution equation for the determinant of the metric, okay? And you will, if you look at that tutorial, see that that time derivative is equal to something like k. Maybe there's an alpha in there. So that means we can replace this k with the time derivative of the determinant, okay? And then we can integrate this equation. But of course, that introduces a constant of integration for which we have to make a choice. And if we make that choice 1, then we get this. Okay, so it's that 1 comes from really a choice. It's a constant. It's an integration variable, a constant of integration. It comes from the initial. Exactly. Yeah. Mm-hmm. Absolutely. Yeah. Okay. All right. Should we call it done? Okay. Great.
Okay.
Thank you all.
Okay. Yeah, so this concludes the lecture part of Thomas's course. Just wanted to extend my warmest thank you to Thomas for coming here and sharing his time and expertise with us in designing and teaching this course. So just a last thank you.
My pleasure. My pleasure.